Welcome to lecture 7, so lecture 7 already, of MCS 472 on industrial math and computation. So what is industrial math again? We are solving problems in science, industry and government. It is also a mathematics course. We are looking at the mathematics, very useful to solving these problems. Mathematics interesting to engineering in particular. So in lecture 6, we introduced the way of looking at signals using the z-transform. So the z-transform was then also in turn very useful to solving recursion relations. So it had a very nice connection with the partial fraction decomposition and with the Lagrange interpolation that we remember from numerical analysis. So in this lecture, we are also considering signals, and we are introducing filters and the concept of the transfer function, very much related to the z-transform, the Laurent series. So the main part in this lecture is on filters, so we will see how to design a filter to remove a signal. And in the second part, we will introduce a more systematic design of filters. And for that, we introduce the notion of stability. And we will show how to compute the amplitude gain and the phase shift of a stable filter. Okay, so let's start with the beginning first. So this lecture can still be viewed as much as possible as self-contained of the previous lecture. So let's start as seeing sine functions. So look at signals as a sampling of a sine function. So later we will get to Fourier analysis and see that every signal is actually a sum of sine functions at increasing frequencies. So here is a sine function, the well-known sine function, but the point of this picture here is to introduce a unit. So most numbers that we will see in this course all come with units, and also even functions. So if we talk about a signal, most signals are periodic, then we measure that in the number of cycles per second. So here I made a point, the horizontal axis, to label it that the unit time from 0 to 1 is expressed in seconds. So we are looking at a sine function over the interval 0, 1. It's the sine of 2 times pi times t. So the legend, the label here, and it's unfortunate, so this is already my first slide that I have to correct. So it's the sine of 2 times pi times t. So the legend omits the 2 times pi. Okay, so I have adjusted the grid. The grid is within 0, 1, so perhaps it's not entirely clear if the resolution is not that fine, but you can see it from the ticks on the horizontal axis. The sine function will be sampled at a frequency of 8 Hertz. So 8 points per second. Okay, so we will see a sequence of numbers. The numbers are sampled, computed by evaluating the sine function, the sine 2 times pi times t. So sampling at u naught, so we call u naught is the first sample, which is just 0. Then we have u1, the sine at 2 times pi divided by 8. Then the sine of 2 times pi divided by 4, which is pi over 2, which is 1, etc., etc. So we have a signal now, a sequence of numbers obtained from sampling at 8 Hertz. So this is our numerical input data. First exercise, it's very much connected to the previous lecture. So what is again the Z-transform? So the Z-transform is the Laurent series starting at u naught and then plus u1 divided by z plus u2 divided by z squared. So what is the Z-transform of a 1 Hertz sine function sampled at 8 Hertz? So one now looks back at the previous slides, one looks at these numbers. So we have a sequence of 8 numbers repeated. So every second we see the same sequence of numbers again. So remember one of the previous exercises. What is the Z-transform of the signal 1 2 3 1 2 3 1 2 3? So here our signal is u0, u1, u2, u3, u4, u5, u6, u7. Again, then repeated. So the signal last time 1 2 3 1 2 3 1 2 3. For that I suggested that you substitute the z by z to the power 3 or z to the power 2 if you were in class. So that inserts extra zeros. So you apply that same method again, and you can leave the u0, u1, u2 symbolically, resisting the urge to simplify the u0 by, although I think symbolically the signs at pi over 2, pi over 4, etc., etc., are actually all kind of nice expressions for that. Okay, so the purpose of this exercise is to connect with lecture 6 on the Z-transform. Okay, here is another signal that we had. That was the delay. So in here actually you see again the definition of the Z-transform. So one does not need to go back to lecture 6. So we have an input, and the input is just a series of numbers, and we look at this Laurent series. So again, why do we do this? With the Laurent series, if you look at the expression that it represents, the poles, the roots of the denominator, should not yet talk about poles, they will come in later, but the roots of the denominator will actually express the main characteristics of the sequence. So we can often tell from the sequence, is the sequence constant, is the sequence growing or decaying. So that was the main purpose of looking at the Z-transform. Okay, so we have covered delay. So here I will present delay again. So we have two signals, the original signal and then the delayed signal. So in lecture 6, I'm then, by the definition, I said that the Z-transform of the delayed signal is the Z-transform of the original signal divided by Z. So here this is worked out a little bit more formally than last time. But the point of this slide is it's not just all repetition what we do in this lecture. So the point here is a different viewpoint. We view now the z to the power -1 as a representation of a filter. So we can have a filter that takes an original signal, but then kind of pauses at the beginning a little bit. So we just don't do anything in the first signal. So we can see this as a filter. So that's our first example of a filter. It's simply delaying the original signal, and we will see that it can already be useful. All right, what is now a filter? So a filter makes a new sequence out of a given sequence. So there is an input and an output. All filters that we will consider, at least in this lecture, all filters are linear, time invariant, and there are causal. So these are three words which will be specified in this definition. So linear means that the filter applied to a linear combination is the same as the linear combination of the filter applied to those two signals. So that is the linearity, quite familiar from our linear algebra. The time invariance means that if we have a lag, if we have a delay, so for all the indices greater than some k naught, we have the same sequence of numbers. So if we are delaying the signal, the output will be also delayed. So we are delaying the signal with k naught, then actually also the output gets delayed by k naught. So it's time invariant. If we know what the signal does for one period of time, then we know what it does for another period. So that's why this is very useful to deal with periodic signals. Remember the Hertz unit. Then the last property, causal, means essentially that you cannot make anything from nothing. So if your input signal is 0 for a number of inputs, then your outputs will also be 0. That's the causality. And that's also a very natural property. Okay, the second exercise mainly asks you to reflect a little bit on these three properties. For the first example of the unit delay. So the unit delay we represent here by this 1 over z, which seems strange, but again, so this is the symbol for the z transform. When we think about a signal or a series of input data, it's often much better to think about in the frequency domain, not in the time domain. So that's why we represent also the unit delay by the z minus to the power -1. So the z to the power -1 does not mean that this is t to the power -1. No, this would not be this would then be non-linear. You would have a hyperbole up there. No, just show that the unit delay is linear. So if you have a linear combination of two signals, that if you delay the combination of these two signals, that this is the same of combining the delayed signals. So it's time invariant. So what that actually means that if there is a periodicity in the input signal, think about the sine again, then you will see that periodicity also in the delay, but you will see it with a delay. So here you actually use the definition of the, so yes, so this is the importance of this exercise. It looks like it is a play of words, but it is important when you solve this exercise that you apply the properties using the unit delay. So you use the recipe for the delay. So you, for each property, you write the definition of the output of the y's, and you see indeed that they follow the properties. Okay, what is now so important about these linear time invariant and causal filters? Well, if you know what the filter does to the unit, so here assume that the unit, so the unit impulse is a very basic signal. It's 1 and then it remains 0 for the rest of time. If you know that the response, if the filter then returns h1, h2, h3, so we call this the impulse response, and we write it as the letter h, also as f followed by the delta. So delta is our symbol for the unit impulse, the little delta. So the theorem says that, and we're going to prove this. It's not that hard. The theorem says that the impulse response determines the linear time invariant and causal filter. So if you know the coefficients in of h, and h is again a series, then actually you can compute the output. So if somebody, again, this doesn't seem much of a help here because, hey, you have to remember a sequence of numbers. The h is a sequence of numbers that stretches on forever. How is this helpful here? Well, we will use the z transforms. That's the short answer. So that's another illustration for the usefulness and for the purpose of working with these Laurent series. We also have a recipe. So convolutions play an important role, and convolution, if you have ever multiplied two polynomials with each other or two power series with each other, then you have already computed a convolution. So the word convolution sounds convoluted, but it's the operation of computing the output from here now the impulse response. So the values for h are the impulse response, and the u's are again the symbols that we use for any input. So given any input and given the impulse response, you can compute the values of the output by computing the convolutions. Okay, this is important. So to work with this, we actually work with the Z transform. So the Z transforms give us very compact representations for signals in the time domain. So we define, we look at the transfer of the, we look at the Z transform to the impulse response. And actually, there is another mistake here. I was a little bit too quick. So the Z transform of the impulse response is this hz. So you shouldn't have used the transfer function here. So if you have this Z transform of the impulse, then actually you can write the Z transform of the output as the product of two Z transforms. So the Z transform of the output is the product of the Z transform of the impulse response with the Z transform of the input. And the Z transform of the impulse response is the transfer function. So the definition here properly defines the transfer function. So ignore the word transfer function earlier on the slide. Okay. Here an example, and we've computed this example already. So we've seen our first filter was the unit delay. What is now the transfer function of this filter? Well, why was the picture using z to the power -1? Well, z to the power -1 is the transfer function of our unit delay filter. So here I do this with the definition. So what does the unit delay filter do to the impulse response? So remember, so these are all words here, of course, but the purpose of the slide is for you to kind of get familiar with the word transfer function and Z transform and impulse response. So the sentence here, what does it mean that the transfer function is the Z transform of the impulse response? Well, look at the impulse response. So the impulse response, we also just defined it, is the response of the unit signal. So we're just going to insert 1, 0 to this unit impulse. Okay, so then what is the Z transform of this? Well, we look at the Laurent series. So here we have actually the Laurent series definition of the input. So the Z transform of any sequence U is defined here. So we see that there is only one coefficient different from 0 in the delayed unit signal, unit impulse. So, and that occurs with the second one. So the first one is the constant, so we have the z to the power -1. So in some sense, this slide restates our property of the z transform of a delayed signal. So it all, in a way, what we just defined makes sense, but what we knew already. It does not contradict the statements. So also the property here that we can write the output, so the z transform of the output as the z transform of the input divided by z, this corresponds. But now it is formulated within the language of filters. Okay, so I said that we would prove this theorem. So what was the theorem again? So the theorem was saying that in a linear causal time invariant filter, that the impulse response entirely determines the outcome of the filter. So let's prove that statement. So we have any input, and we can actually take these delayed unit impulses as a basis. So we can write any input as a linear combination of these delayed impulses, unit impulses. What does that buy us? Well, it makes that we can apply the linearity. So if we apply our filter to this linear combination, then the outcome is a linear combination of the filter applied to these delayed unit impulses. Remember, we are looking for an output already. And actually, this is the theorem. I'm just going to derive now again the convolution. So in a way, I have now just by the linearity shown that you can write the output, the entire output, so it's an infinite sequence, by the input combined or multiplied with the output of the shifted impulses. Okay, so how do we do this now computationally? So where do the convolutions come in? So I had the big sigma where as an expression for y. So let's write it out. So remember our notations. So slides, they glide away, and we were using the H0, H1, H2 as the output of the unit impulse. So the H0, H1, H2 is the impulse response. And we're going to write it several times now. So I stop here after 3 times. And make the combination. So the first signal, the first time, it's actually quite simple, U0, H0. The second one is U0, H1 plus U1, H0, etc. So you see the convolutions coming in. The same as you compute the coefficients of a product of 2 polynomials. So we just proved the theorem. So in this sense, this is a great mathematics course. In every mathematics lecture, there should be a proof. Actually, there will be 2 proofs. So the content of this lecture is in one sense introducing important terminology. So we have seen the concept of a filter and its transfer function. But the other important thing is to show that mathematically it all makes logically perfect sense. All right, but we want to process something, so we would like to solve some problems here. So let's get to it. So we've seen early on that, and I still have to fix here this sine of 2 times pi times t. So we have our signal sampled at 8 Hertz. And suppose that we want to remove it. Suppose that, hey, this is some noise that we don't want. How can we do this? Well, observe that it's a periodic signal, and if we look at the delay here a little bit, so the signal repeats itself, so that's why I'm only writing the first 9, so the U0 and then the U1 goes on again. But observe that there are also the zeros there. We don't really need to do anything to remove those. But then we have the nice symmetry of a sine function. Okay, so what good does this do? Well, we could actually see that after half a second, the signal already repeats itself, but then with a flipped sign. So there's more structure to the sign than just this periodicity, than just it starts to repeat itself. And we can exploit this in removing the signal by combining the delay signal. So what we do is we, in our filter, we wait for time units, and then we add those 4 delayed units to the original signal. So let's do this here. So that means that our first numbers, then the first four numbers are then 0. And we do this all over again. So we have this symmetry. So the negative numbers are then compensated by the positive numbers in the next half cycle. So what does this mean? Well, we have seen that delaying once, the unit delay, is multiplying by z to the power negative 1. Delaying 4 times is multiplying with z to the power negative 4. So we can write down now the z transform of the output as the z transform of the input plus the z transform of the input divided by z to the power 4. So we have the description now as our output as a product of the input. So if we factor out, it all works out extremely nice. We can factor this out, and you see that we have our first filter, so a filter that actually does something. It removes the signal. The signal then has a very nice transfer function. And it's, if you like, it's also the description, a mathematical description of what the filter does. It does an addition and it does a delay. So we combine the original signal, the one, here with the delayed signal. So there's a very beautiful way to describe this as well. Okay, so what good does this now? Well, this actually is very useful. We often have that the noise is happening at a very high frequency, or I should actually say this in the opposite way. So we can actually use this, what we did on the previous slides. We can do this now to remove high frequency noise. Here is the exercise. So it's formulated in the language that I'm trying to introduce. So in a way, the exercises, they are linguistic of nature. They are meant to make you familiar with the terminology. But it's just a repetition of an adaptation of what we have just seen. So what have we seen? We covered the removing of a signal of 1 Hertz sampled at 8 Hertz. Here you consider now a signal running at 60 Hertz, and we're going to sample it 12 times faster. So the notations need to be adjusted, and you will need to also use the property of the sine function. So actually the signal here, so the exercise is that it's not just any signal, so it's a sine function sampled at 60 Hertz, running at 60 Hertz. So it moves extremely quickly. It moves 60 times faster than our sine function that we have seen. Now there is a second question there. The problem with filters like this is that they are going to remove anything. So by using this property, adding a delay to this, so they're also going to remove other signals. And that can be there is a remedy to that. So here in real world, if you watch Western movies, then you often see that the wheels of the wagons, they kind of move in the opposite speed. So this has to do with the frequency of the camera. The sampling often is done there at read somewhere at 24 hertz, and you actually have the same picture of the, but in a shifted position. That looks very unnatural. Often it looks as if the wagon is moving backwards, opposite to the natural flow. And this can be explained by uh, the sampling rates, the sampling rate of the camera. Okay, I have 15 minutes left. I will not use them all. In the next lecture, we will go into the design, the systematic design of filters, and I will introduce another main theorem of filters. But let's look at what type of filters that we want. So that's another characterization. So our filters are linear, time invariant, causal, but they also should be stable. Stable means that if you have a bounded input, then the input will actually remain bounded on the output. So a bounded input will yield a bounded output. So again, just for clarity, what are bounded input and outputs? Well, here are three example signals. The constant signal, 11111, is obviously bounded. Also, any constant signal remains bounded. What is not bounded is the exponential growth, but then exponential decay is again bounded. Okay. Here is a characterization of a stable filter. So the filter is entirely determined by the impulse response. The impulse response coefficients then determine the transfer function. So if the sum of all the coefficients in the impulse response sum up to a finite number, then the filter is stable. So this property says again that if you know the transfer function of a linear time invariant causal filter, then also that is going to determine the stability of your filter. So proving this proposition would lead us too far into analysis, but the transfer function actually converges as a Laurent series to a continuous function for all arguments outside the unit disk. Here now, the unit disk, we are thinking with complex numbers. And that is now the main important topic of the rest of this lecture. If we do have a stable filter, what is the output? So we think of our signals as periodic. So the input comes from a sine function sampled at a specific rate. So if the filter is linear, time invariant, causal, then the output is also a sine function. And that's kind of at first kind of surprising. It's a sine function, but it has a different amplitude. So there is a gain in the amplitude, and there is a phase shift. And how can we compute this? Well, perhaps you guessed it already. We have the transfer function that entirely determines what our linear, time invariant, and causal filter does. So we can derive the amplitude gain and the phase shift entirely from looking at our transfer function. So I've tried to tell this theorem in a natural way, but let's look at it again. So we have an input. So we look at a sine function. So at the beginning we had 2 times pi times t, so we had 1 hertz. We sampled it at 8 hertz, so we had a sampling rate. And we looked um, at the samples. That was the input. So at least the input should be familiar here. Um, the point is that the little I here in the notation of this theorem is indeed the imaginary unit. Um, so complex numbers, we often introduce them in a very abstract manner in mathematics, but they appear extremely naturally when we think of signals. So complex, so they are far from being imagined. They are, in some sense, quite necessary in the treatment of data. Running ahead over the preview of our next lecture, we will define and actually design filters by deciding what do we want as a gain. Do we want to amplify our signal or do we want to dampen it? And there is also this shift that we may want to steer. Okay. All right, so let's look at the proof. So we were looking at our signal. So we had we had the signs that came in and the input, but it turned out that we had to evaluate the transfer function at e to the power I times omega times t, where omega captures the frequency of our input signal and the t is the sampling rate. Okay, so with hindsight, let's start with this e to the power I omega t. And let's see what the filter does to this signal. Well, we have the transfer function given to us, so that was the capital H. The little h are the coefficients that appear in the convolution. So the kth number in our output is computed by this convolution formula for any input. But actually now we are not interested in any input. We are interested in what does the filter to this signal that is this complex exponential. That is this exponential. Okay, so let's rephrase this a little bit. And we want to get the transfer function in there. So we want to get h evaluated at this s. And you see we're almost there. Because remember the definition of the transfer function again. So the purpose of this whole lecture is to ease you into the notation and the terminology of working with Laurent series and thus working with Z transforms and transfer functions. So you see that we recognize, perhaps not at this point yet, but we are recognizing the definition, but it's truncated at k. So the definition works for a sequence that goes on forever. But we can fix this. So we fix this essentially by taking the k as large as we like, as large as necessary. So also here it's important that we work with a stable filter. So also the absolute value of s, it's an exponential, where we have this purely imaginary part. So there is actually also a unit amplitude here, if you like. Okay, we're actually almost there. So we have an expression for our output, and we still want to find now our sines sitting in there. Well, what is the relationship now with the sines and the complex exponentiation? So most likely you may have seen Euler's formula. So this is here Euler's formula applied and combined. So if we have S, then if we apply Euler's formula, we can write this as a complex number. So in a way, this is the notation for a complex number with angle the omega times t. We combine and we get our sine function in there. Or we get the sine at k times omega t. So this is our sample. So the sine k omega times t is actually our input. So perhaps I should have, so this is actually the main point here. So the slide looks kind of trivial as far as the mathematical manipulations go. But in terms of our theorem, what is the last line here? So the last line is our sampled input. Okay, now I still have 5 minutes for the last slide, the conclusion of the theorem. So we have already derived, so for sufficiently large k, we have that the output, the kth output, is s to the power k times our transfer function. Now suppose that we want to write the transfer function evaluated at s. So the transfer function is defined like this. So if we have this transfer function defined like this, we can compute with a very simple manipulation. We can define the amplitude gain and the phase shift. So indeed, we find the expressions of our theorem, the expression for the amplitude gain, which is the magnitude of the output, and then also the correction term, if you like, in your phase shift. So that we call the phase shift. So that's the argument of this. So what we also derived is an expression for the output. So the yk here corresponds to the reformulation of the input.